Yeah, here in this video we are solving two or three simple questions based on moving charges and magnetism. The first question is this: Biot-Savart's law gives an expression for the magnetic field strength of infinitesimal current element ideal of the current carrying conductor only, right? So this is a correct statement actually. So if you try to understand what he has given for you, what is Biot-Savart's law? Let me try to explain. When a current is passing in a conductor, we have a point P who is at a distance r, making an angle theta or d theta. Due to a small portion of that conductor dl, due to this current carrying conductor at this point P, there is a magnetic field that is directly proportional to I dl sin theta by r square. Proportionality can be eliminated with constant mu naught by 4 pi, and this law is the Biot-Savart's law, right? Therefore, that statement is correct. We are going to calculate magnetic field at a point due to a small portion of the wire due to a current carrying conductor. So the first statement is perfectly fine. Look at the second statement. What the second statement says is Biot-Savart's law is analogous to Coulomb's inverse square law of charge q, with the former being related to the field produced by a scalar source. So scalar source ideal, whereas the later being produced by a vector source q. First of all, these are not analogous to each other. Something like Coulomb's inverse square law is to find the force between the two charges separated by a distance f, that is mu naught by 4 pi q1 q2 by r square. So this is the force due to the electric charges. This is the field due to a current carrying conductor. Therefore, they are not analogous. They are not similar to each other or something like that. So I disagree with this is analogous. Therefore, I would like to say second statement is wrong and first statement is correct, and hence this is the correct option. That's one question. Let's have a look at the other question. From Ampere's circuital law, for a long straight wire of circular cross section carrying a steady current, variation of a magnetic field inside and the outside regions of that wire is. Therefore, we shall consider a long straight wire first of all. Second question we are talking about. We are considering a long straight wire carrying a current I. Due to a small region, how much is the kind of the strength that we are trying to calculate. Let's imagine a small region, so which becomes automatically some kind of a cylindrical surface. You know that within it has been derived that if we have a point distance r, and where you are trying to calculate a magnetic field within that surface, if you are having a point that's having a distance less than that of the radius, B will be increasing in a proportionate way, that is within the radius of the cylinder, where this is the radius of the cylindrical part. You go beyond that, it will be start decreasing, that graph will go like this. So there beyond that, B is inversely proportional to R. If R is greater than radius, B is directly proportional to R if that R is less than the radius. So that, let us see which option is explaining that. Linearly decreasing function distance up to the boundary, that is wrong. Uniform and remains constant, that is wrong. Linearly increasing function of the distance up to the boundary of the wire and then decreasing outside the region, okay. Linearly increasing up to the distance r up to the boundary of the wire, 1 by r depends. So the last option is given in a more accurate way, wire up to 1 by r dependence for the outside region, increasing up to r boundary of the wire, 1 by r dependence for the outside region. So option D is the more appropriate answer. That's how we pick up the answer for the second question. Let's have a look at the last question, a small question. A long solenoid wire of 1 millimeter has 100 turns per millimeter, right? So that the solenoid means a kind of a non-conducting material around which a wire is wound like this, and when a current is passed inside the solenoid, there is a magnetic field developed. How much is the magnetic field developed inside the solenoid? We have derived a formula, that is mu naught n I, where n is the number of turns per meter, but what is given for is 100 turns per millimeter. I have to convert that into meter. 1 millimeter is 10 power minus 3 meter, that is 10 power 5 turns per meter. Mu naught is known and I is given for you in the problem. Current is 1 ampere. That implies magnetic field is equal to mu naught, that is 4 pi into 10 power minus 7. And then n, as we have calculated, 10 power 5. Current I is 1 ampere, that is 4 pi into 10 power minus 2. Pi is 3.14, and so if you multiply it becomes 12.56 into 10 power minus 2. Being magnetic field you are calculating, that is Tesla. That's how we solve this question. Thank you for watching.